This lesson will cover parent functions. The learning goal is to graph parent functions, linear, quadratic, square root, reciprocal, and absolute value, and success criteria is you can identify key points for each function and sketch a general shape. Now, graphing functions requires a keen sense of transformations, but also the base functions themselves. This unit will explore graphing transformations, 5 basic functions. Some you're familiar with, such as the linear and quadratic functions. Others may be new to you, such as the square root, reciprocal, and absolute value functions. Every function has characteristics and key points that define the base function that help us graph the transform versions. Now, domain and range are also very important to these functions. Now, we call the base functions parent functions. Each parent function is of the form f of x. A parent function, which is with transformations, is of the form a times f of k times x minus d plus c. Now, we'll explore transformations later, but all of these variables are transformations acting on our function. You may be familiar with this. So this looks like vertex form in a way of our quadratic functions. So we're going to look at many of these parent functions. The first being the linear function. Now, a linear function you guys are very much familiar with. You might think of like, y equals 2x minus 1. But we want the parent function, the most base version. That is just y equals x. And if we have an equation for one of these graphs, we can create a table of values. Now, of course, for a linear function, we are very much familiar with what this one looks like. We just pass through 0 and go from negative infinity to positive infinity. But if we did look at this as a table of values, you could get your key points. So we have x and y, and we have negative 2. Since y equals x, all these values are exactly the same. It's really the key feature of a linear function, the parent linear function, is that all the coordinates are equal. Now, domain and range, remember domain and range, that's kind of stating where x can be and where y can be. Domain is where all values of x that you're functioning equal, and range is all values of y that you're functioning equal. Now, domain and range are written with specific notation. We use the curly braces to kind of show that this is a domain we're looking at here. And now for domain, we say something like this. So we look at our function and we think, okay, x can pretty much be any value. So if x can be anything, then we say x, and we say this little e, this is epsilon, and then we have this kind of strange looking r here. This is saying x is an element of all real numbers. So epsilon, this e is an element of, and then this r, this is saying real numbers. So this is basically saying x is an element of all real numbers. X can be any number as long as it's a real number, which pretty much all numbers you are working with in this course are. It is a part of this domain. Now, range, if you look at the graph again, these arrows show that we're going infinitely up towards positive infinity, infinitely down to negative infinity, so we can be any y value. So y is an element of all real numbers for our range. Now let's look at the quadratic function. The base function, the parent function for a quadratic, is y equals x squared. No surprise there. If, again, we needed to make a table of values to find our initial points here, we have x and we have y. So usually when I do the initial points, I always use -2, -1, 0, 1, and 2. And if we plug these into our equation, so x squared, so this here would be -2 squared, and that's 4. -1 squared is 1, and then 0 squared is 0, and then we have 1, and then 2 squared is 4. So this gives us our initial points. So we have 0, 0. We have 1, 1, we have -1, 1, and we have 2, 4, we have -2, 4, and then we can create our curve here. If arrows point up. Remember, always put arrows on your function. If your function is going to be continuously moving or progressing in that direction, you need those arrows there. So here's our quadratic function. Again, this is a throwback way back to grade 10. Our quadratic function is, again, one of the base functions that we need to be working with. Now, it does have domain and range. X can be any number for our parent function. So our domain here is x is an element of all real numbers, can be anything. Let's look at our range here. So our function starts at its most key point, its vertex, and it progresses upwards. So it opens up, so it cannot be negative here. Our parent function can't be negative. So we say y is an element of all real numbers, but we have a restriction. So we have this little vertical line here. This means such that. So that's such that, and then we say y is greater than or equal to 0. So that's my range here. It says y is an element of all real numbers such that y is greater than or equal to 0. Or we can say something like y can be any y value as long as that's positive. So this is a notation we do need to be using. So do make note of this on how you write your domain and your range. If you have restrictions, use the vertical line for such that, and then you state your restriction afterwards. Oh, I have two linear functions here. Let me just check something here quickly. Okay, let's just skip this. I don't know why that's there. Let's go down to the square root function here. So we have the square root function. So we know what the square root sign is. This is the square root. The square root function, its parent function is y equals the square root of x. So this is our parent function for a square root function. Now, the square root function has a very particular restriction on it. Because it is a square root, the restrictions of a root does act on this. So if we were to make, for instance, our table of values, and we use those same values I was using earlier, -2, -1, 0, 1, and 2, well, we'll notice when we plug -2 into our roots, we're going to get an error on your calculator. You can't do this. So right away we can tell that the square root, we can't have negative values there. It's already a restriction on our domain here. So let's start with 0. So 0, and then the square root of 0 is just 0. So that's one of our points. And then we have 1. So we'll do the square root of 1. Well, square root of 1, from what we saw before, it could be positive or -1. So we know with roots that, for instance, if you do the square root of 4, that's equal to +2 or -2. Now here's the thing that with the square root function is if, let's say, it was, in this case, +1 and -1, well, all of a sudden we fill the vertical line test, and this is no longer a function. So if square root functions, whenever you root your whatever's inside your root here, so your radicand, when you take the root of your radicand, you're going to use the positive result of this. So root of 1 gives us 1, so 1 is one of my points. Okay, let's do 2. Well, if I do the square root of 2, that gives me 1.414, blah, 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 and that's a irrational number. I kind of want to avoid doing that. So I'm going to avoid using x values which are not perfect squares. So our key points for our root function, square root function, is we want to use perfect squares for our x values. So 4 is an x perfect squared. Root of 4, that's 2. And then our next perfect square for x is 9, and the root of 9 is 3. And you might sort of realize, hey, wait a minute, this is kind of reverse of our quadratic function here, where we had 0, 0, 1, 1, 2, 4. Now it's in reverse. 0, 0, 1, 1, 4, 2, and 9, 3, where the y and the x values are exchanged. So when we are working with a square root function, just pay attention to your x values and ensure that you are using the perfect squares for your x values for the parent function. So here we can connect our dots. It is a curve. It curves up towards positive infinity. Slowly, but it will get there. So this is our parent function for the square root function in its graph. Its domain, as we saw, it cannot be negative. So we say x is an element of all real numbers such that x is greater than or equal to 0. So x can be 0, but it cannot be less than 0. And then we have our range. We can see here that we do not have any negative values, so our range is y is also an element of all real numbers. such that y is also greater than or equal to 0. When you're writing the real number symbol, if you do an r, that's fine, but try and put that extra little line beside the r. Sometimes I kind of include it when I'm writing the bar itself. With a little kind of extra r shows that this is the real number notation. Next we have the reciprocal function. Now the reciprocal function, well, it's reciprocal, so we know, for instance, if we have 2, the reciprocal of 2 is 1 over 2. So if we have an equation, let's say x, the reciprocal would be 1 over x. So the reciprocal function, its parent function, is 1 over x. I should say y equals y over x. There we go. So y equals 1 over x. And then let's get some points here. Oh, that is a Cartesian plane. I need a t-table. Okay, here we go. So we have x and we have y. Let's get our values back in here. So -2, we have -1, 0, 1, and 2. So if we plug these values into your equation, so for -2, that's 1 over -2, so that's -1/2. And then -1, so that'd be 1 over -1. That would give us -1. And then we have 1 over 0, and all of a sudden things just explode. So we can't divide by 0. Remember, that is a rule for 0. You cannot divide by 0. So what happens in the reciprocal function is there's a kind of like a break in the graph. And this break, so we draw then, it's a vertical line at x equals 0. So we're basically drawing the line x equals 0 here. This line here, actually should do a dotted line actually. Usually we do these as dotted lines. This is called an asymptote. And it is horribly difficult to remember how to write this word. Over time, if you keep on writing it, you'll kind of remember, because it's just weird. So this is called an asymptote, and an asymptote has a very particular feature. It cannot be crossed. So your function, if it were to approach it, it can't go through it. It cannot go through the asymptote. It approaches, and all of a sudden it just veers off towards infinity, and it tries to get as close as possible, but it cannot touch. So you'll see more about why that happens later on. But for an asymptote right now, just note that your curve will come really close, but will not touch. So it comes close, but okay, I should say will not. It usually doesn't touch, and there's a reason behind that. Usually, you'll see that later. For this course and this year, it will not touch the asymptote. There are some instances later on that you'll see, but that actually happens for this asymptote. So we have actually two asymptotes here. There's a vertical one and a horizontal one, and both of them for the parent function lie on the axes. So let's get back to our points for a minute, and then we'll sketch this. So here we have 1, and here we have 1/2. Now, just to show you what happens here is, let's say we picked negative, let's throw it in here, negative 1,000. So if we plug negative 1,000 here, then we get 1 over negative 1,000. And that gives us negative 0.001. If we do 1,000, then we get 0.001. It's very, very close to 0, but it's not quite there. So if we have an x value of 1,000, way off, you can't even see it, like way off the screen, it's going to be very, very close to 0, but it's not touching it. If I do 1 billion, again, it's going to be really close to 0, but it's not touching it. So that's why we have this horizontal asymptote here, because no matter what value for x we put in, we're not going to get anything for 0. We're going to approach 0, but we're not going to touch it. So our first key point is 0 itself for the parent function. That is an asymptote. That's our vertical asymptote. That's right here. And then as we plug in very large positive negative values, we see what's happening as we approach the infinities for x. Is we're going to get very, very, very close to our x-axis, but we're not going to touch it. So let's plot the points we do have. So we have 1, 1. If my pen there decides to work again. We have 2, 1/2. We have -1, 1. We have -2 and -1/2. So we can kind of see what's happening here, but we want to go a bit further. Let's get some more values in here. Let's get 0.5 in and -0.5. So we plug these values into our equation. 1 divided by 0.5, that's 2, and 1 divided by -0.5, that's -2. So that gives us these values here. Again, we can kind of see the shape here. If you plug in more values, you'll start to see more and more. As our function approaches the lines, it starts to curve towards it. It's not going to touch it, but it's going to curve towards it. So let's change colors here so we can see that. So here's my function. It's coming. I should start from the left, actually. So it comes from negative infinity, very close to our asymptote. It's going to curve through all of these points, approach the vertical asymptote, not going to touch, and go down towards negative infinity. And then that does this. It hops over the asymptote, comes down from positive infinity, curves through these points, and then hugs the x-axis, the horizontal asymptote here, as it moves towards positive infinity for x. So it is a very strange function when you first start to learn it, but you'll get used to it. Your key points for a reciprocal function, which you might sometimes hear referred to as a rational function, because it's a fraction, it's a rational value. The key points is 0, 0 as one of your asymptotes, 1, 1, and -1, -1. These points kind of tell you where your curves are going to be. You know this function is going to curve. You basically look at your quadrants, and you're going to have two curves in situated in kind of like the quadrants that your asymptotes create. So those points will help you determine where your curves are going to be and how they're oriented. So for domain, we have a very interesting way of doing domain and range here. So domain is x can be all real numbers such that x cannot equal 0. So we have to say x can equal 0. For range, we have y can be all real numbers such that y cannot equal 0. Because those asymptotes, these areas of the graph where a function cannot be, the way it curves, we cannot equal these values. So that is our parent function for the reciprocal function. And finally, we have the absolute value function. This one is also a very interesting one. The absolute value function looks like this. The equation is y equals, and we have this symbol here. So we have two straight lines with an x between. This here, this is, whoa, my pen just went veered off into who knows where. So this is absolute value. Now the absolute value basically states this. The absolute value, and my pen starts to work in. Oh, here we go. The absolute value states that anything inside the absolute value is the magnitude, the size of value, that value. So absolute value of 2, that's 2. The absolute value of -2 is also 2. It basically takes your sign. It says, I don't care what the sign is, whatever the value here is in size, that is what you're going to equal. So the absolute value of 2 and -2 are both 2s. So if you have a negative, it becomes positive, and if it's positive, it remains positive. Think of it in that way. So let's make a table of values here. We can use our original points of -2, -1, 0, 1, and 2. So the absolute value of -2, as we saw, is 2. The absolute value of -1, so it's -1, so it becomes +1. Absolute value of 0 is just 0. Absolute value of 1 is 1, and then 2 is just 2. So let's plot these points. We have 0, 0, 1, 1, 2, 2, negative 1, 1, and negative 2, 2. And we can see it's kind of like the linear function, but it creates this V shape. So the negative part of the linear function is instead reflected here. It's not a very good line. As our function proceeds both in negative, positive infinity for negative x and positive x. Now, for our domain, again, x can be all real numbers. So we have x is all real numbers. And our range, we can see it has to be positive here. Our range is y exists in all real numbers such that y is greater than or equal to 0. So these are parent functions. For each of them, you can create a table of values to find your initial points. Some have some very specific key points, like our root function and our reciprocal functions. Pay attention to those, and make sure you have your domain and range notations as well.